This is the third module of Unit 6 on thermodynamics and thermochemistry. This module introduces the ideas of spontaneity and entropy. For chemists, spontaneity means thinking about will a reaction go. It's possible to write down a balanced chemical equation with reactions and products, but that doesn't mean that the reaction will actually happen. Essentially, a process is spontaneous if it happens, quote unquote, on its own, or without adding work to make it happen. In chemistry, reactions that tend to go on their own, without adding work or doing something to make it happen, include exothermic reactions. You've seen in your personal experience in the laboratory and real life that once you get a fire going, for example, it will keep burning. In general, there is a tendency for exothermic reactions to be spontaneous. Remember, exothermic means delta H is less than 0 at constant pressure. Processes which cause an increase in the entropy of the system also tend to be spontaneous. To understand that, we should need to talk about what entropy is. Entropy is often thought of as disorder, and you'll see that discussed in texts. But entropy is really a thermodynamic quantity related to the number of microstates of the system. The system, again, is whatever you're looking at. Entropy could be thought of, for example, as the number of microscopic positions of particles. Let's consider a simple example in which we have 4 gas molecules, colored in this case so you can tell them apart, occupying a volume of 2 globes and joined together at the neck. Given 4 particles and a volume 2 globes, you can essentially, in terms of position, roughly define microscapes by noting the number of balls on the left and the number of balls on the right. Here, for example, is a quote-unquote microstate where all 4 balls are on the left. Here's another where all 4 balls are on the right. These are both possibilities in a situation in which you have 4 particles occupying 2 globes. 4 particles or 4 balls occupying 2 globes. You will see more arrangements if you have 3 of the particles on one side and 1 on the other of the 2 globe arrangement. And there are essentially, you will see 4 possibilities for 3 on the left and 4 possibilities for 3 on the right. And you'll count a total of 6 possibilities with 2 on the left and 2 on the right. So roughly speaking, we have 16 microstates here, corresponding to the macrostate, 4 particles occupying a volume of 2 globes. Notice that the number of microstates corresponding to situations in which all the particles are on one side or another is small, and yet there are 6 microstates where they are evenly distributed. All things being the same, it's much more likely, given each one of the microstates would be equally likely, to have the particles evenly distributed than on one side or another. Actually, as the number of particles increases, the likelihood of this even distribution increases. And the likelihood that you will find all the particles on one side of another is vanishingly small. For example, if it was 4 moles instead of 4 particles, the likelihood that all 4 moles would be on one side or another would be extremely small. But all of these, they're varying, all of these arrangements, given and with all their relative probabilities, make up the complete number of microstates of the system. Which is a measure of the entropy. In general, more probable arrangements, you'll see even distribution of particles, are also the quote-unquote more disorderly arrangements. You may think that distributed particles is more disorderly than having them all on one side or on the other. Another way of thinking about microstates or thinking about energies of particles within a system. For example, in this model system, here we have one in which the total energy is 0. There are 6 particles in the system, each with an energy of 0. The number of microstates for this system would be the ways to arrange such 6 particles so that the total energy is 0. You see that there is one way to do that, one microstate. If you allow the total energy to be 9, for example, well, you could put all 9 units of energy into one particle. There are 6 such arrangements. You can have 3 particles with no energy, 2 with 1, and 1 with 7. There are 60 such arrangements. There are 80 such arrangements in which 2 particles have 0, 2 particles have 1, a particle has 2, and a particle has 5. And there are many other possible arrangements of energies for each particle that sum up to a total energy of 9. So if the energy is 9 for 6 particle system, there are many more ways to arrange the energy, many more microstates for the system than if the energy is 0. From this example, we learn that the number of microstates and hence the energy of the system should increase as you add energy to it. In general, processes increasing the number of microstates tend to be spontaneous. For example, if we confine 2 particles to one globe, we have, roughly speaking, 1 microstate. If we open a stopcock and allow the 2 particles to occupy a volume of 2 globes, roughly speaking, we have 4 microstates. And there are 2 with particles distributed versus 1 with all particles on the left and 1 with all particles on the right again. Increasing the number of, so here we see in this example, increasing the volume of a system increases the number of microstates and hence the entropy. You will see that as an example with gases. Gases expand from smaller volumes to large volumes. The process increases the entropy and is spontaneous. Mixing is an example of a process that looks like it creates disorder. Actually increases the relative number of microstates compared to unmixed substances. For example, here we have a sample of blue gas. If it's allowed to expand to fill a volume, a greater volume, its entropy increases. Or we can imagine a red gas on the right, which is allowed to expand to fill a greater volume, and its entropy increases. Mixing can be thought of as a volume expansion for 2 gases into the mixed volume. This increases the number of volume, increases the number of possible microstates for particles, places that they can be, and thus increases the entropy. There is a relation between physical phase and entropy, and naturally phase transitions have an effect on entropy. In general, the number of positions and energies accessible to the particles in a solid is smaller than it is in a liquid, and smaller than it is in a gas. Here, for example, we see ice, where all the water molecules hold fixed positions, and it is melted to form liquid water, in which there are many positions available to the particles. In addition, they acquire a variety of possible energies due to motion within the liquid sample. Right, so naturally, this is a process with delta S is greater than 0. The symbol for entropy is S. Entropy increases when ice is melted to form water. Likewise, entropy increases when you take particles that are packed close together in a liquid state and separate them from one another to form a gas. More positions become available. The entropy of the system increases. Right. So let's see. What have we summarized? Let's summarize what we've learned about microstate increase and consequently entropy increase. Let me re-emphasize that S is the typical symbol for the entropy. Right. Microstates in entropy increase as we have seen. Energy is added. More positions become available to atoms or molecules. This amounts to a volume increase for gases in particular is the largest increase in S. We've seen that mixing increases entropy, and that melting or boiling, phase transitions from solid or liquid to gas, or from solid to gas would increase the entropy. Right. Again, entropy is S. You could show that S increases as Q over T. In other words, we know that entropy increases as energy increases. Specifically, if you add heat to a system, Q, entropy increases as Q over T. So heating something up increases its entropy. In particular, for a phase transition, the change in entropy can be shown to be the enthalpy change divided by temperature. In particular, the transition temperature of the material. This means that delta S is 0 for transitions with delta H is 0, and it follows that gases have more entropy than do liquids, and liquids have more entropy than solids. A point we've actually already established or shown previously. Alright, let's look at a quick example of a process where we calculate the change of S. Example, here we have the entropy of melting. Beg pardon, I'll call this the entropy change of melting water. In other words, how much did the entropy change when we go from the solid to the liquid? Okay, well, we know that, the number of microstates goes up and, the entropy goes up. We've seen that in this lecture. All right, assuming 1 atmosphere, this process happens at 273 Kelvin. Right, looking at a data table will tell you that the enthalpy for this process, delta H, is 6,000 joules per mole, or 6 kilojoules per mole. As you expect, you have to put heat into ice to melt it. The process is endothermic, positive sign for delta H. Delta S is 6,000 joules per mole divided by 273 Kelvin, or positive 21.9 joules over moles Kelvin. All right. So notice the units of entropy. energy over temperature, joules over Kelvin, or if we're talking about a mole of substance like a mole of water, it'd be joules over moles times Kelvin. And that for melting ice, as we anticipated from our earlier discussion, the change in entropy is positive. The entropy increases for turning solid water into a liquid or melting water. It's also straightforward to consider a reverse process, freezing liquid to solid. This also happens at 273 Kelvin, the freezing point. Delta H is negative 6,000 joules per mole. And likewise, delta S is negative. So the reverse process at the same temperature, the enthalpy and entropy changes are equal and opposite in sign. Notice that we go from the liquid state to the solid state. The change in entropy is negative. Entropy is decreasing. Alright, here are some practice exercises. Qualitative exercises in determining whether or not entropy increases or decreases. Without putting a number on it, what is the sign of delta S for the following? Or is entropy going up? Delta S is positive, or is entropy going down? And here we see sublimation of iodine. Solid iodine goes to gas. Bromine and 3 chlorines react to make 2 bromine chlorides. All species are gases. We'll assume for all these processes temperature is staying the same. Problem. Let me correct a typo there. Ammonium, which is a gas, ammonia gas, reacts with hydrogen chloride gas to make solid ammonium chloride. And calcium oxide solid reacts with liquid water to make solid calcium hydroxide. This can be accomplished if you have excess calcium oxide and react it with liquid water. Okay, now attempt these, the sign of delta S or change in entropy for each process before continuing. Alright, does entropy increase or decrease? What is the sign of delta S? For the first process, delta S is greater than 0. Entropy increases as a gas is more disordered than a solid. I use the word disordered very guardedly. What I'm talking about is an increase in the number of microstates, of course. For B, 4 moles of gas product produce 2 moles of gas reactant. Gas, as we've seen, is very disordered. There are more microstates available if you have 4 moles of gas than if you have 2 moles of gas. More ways to arrange the particles. Entropy is decreasing from left to right. In general, gas, as we've seen, is very disordered. A gas, as we note, has many microstates. If overall moles of gas decrease, it is a decrease in the entropy. In this reaction, we take 2 moles of gas and we produce solid. We know solid is a low entropy material, is a substance, and the gases has high entropy. Solid is quote-unquote ordered, gas is quote-unquote disordered. The entropy is going down. For taking a solid and a liquid and forming solid, again, we see an entropy decrease. We are taking a high entropy phase, water, and the result of this process is all one low entropy phase, a solid. Alright, it's useful to be able to find delta S for processes other than phase transitions. Standard entropies are tabulated and can be used to find delta S for reactions. Now these are actual entropies for substances under standard conditions. You will have online data tables available to you to seek out these standard entropies. As you will see, they're used much like enthalpies of formation. Okay. Determine the sign of delta S and then find delta S for these two reactions. Well, the sign of A is going to be negative. We take a solid and a gas and make 1 mole of solid. And the sign of B, we take a mole of gas and a half mole of gas and we make a mole of gas. The sign of B is going to be negative as well. Now, finding the numbers, well, you look up the data table and attempt to use them in the same way you would use enthalpies of formation. You may want to attempt these before continuing. All right. Here are the solutions. I said for both, we predict a decrease in entropy as moles of gas are decreasing. Now let's look at some math. Using this the same way you use enthalpy of formation means take products minus reactants. Okay, the product is silver chloride, has a molar entropy of 96.2 joules per mole Kelvin. Note the units. There's 1 mole of it, so multiply it by 1 mole. And the total for products is 96.2 joules per Kelvin. Now move on to the reactants. Alright, here we have an interesting departure. Silver is a free element, and yet its entropy is not 0. Its entropy is 42.55 joules per mole Kelvin under standard conditions. Chlorine is likewise an element, but once again, standard entropies of free elements are not 0. In the case of chlorine, it's 223 joules per mole Kelvin. We multiply that by a half a mole, and our entropy is 11.5 joules per Kelvin. Okay. Notice for a mole of these substances, this monatomic solid and this diatomic gas, the entropy of chlorine, the gas, is considerably larger than the solid. We've seen that entropy, we would predict that gases should have high entropies. Moving on to our calculation, products minus reactants, we obtain negative 57.9 joules per Kelvin. The product value has taken from it the value of the entropies of each of the reactants. Produce a negative entropy change for this process. Here likewise is a solution to B. We take water gas as a gas under standard conditions, 25 Celsius. Its entropy is 188.7. Alright, this is the total entropy of the products. Now this brings up an important point. The product in this reaction is gas. Water vapor can exist under standard conditions, so this is the entropy of the water vapor. Alright, the entropy of a mole of gas is 188.7, but you must be careful to distinguish entropy of a gas under these conditions from the entropy of the liquid. And notice that under these standard conditions, which are 25 Celsius in one atmosphere, the entropy of the gas is much higher than that of the liquid. Okay, moving on to our calculation. The reactants are hydrogen and oxygen gas. Entropies of 130.6 or 205 per mole. Those give reactant entropies of 130.6 and 102.5 joules per Kelvin. Products minus reactants calculation in this case produces a delta S of negative 44.4 joules per Kelvin. Again, the entropy is decreasing. Again, to get the correct answer, you had to note the phase of water, which is gas. If you had used data for liquid water, you would have gotten a much more negative answer. Alright, this concludes the lecture for Module 6B.